Hi everyone, this is Varun, and today I'll be presenting on Lab 5, Faraday's Law, the last one. So what is Faraday's Law? In simple terms, Faraday's Law is the fact that an EMF can be induced in a loop of conducting wire if the magnetic flux through the loop changes with time. Lenz's law was also key in this lab, and it essentially states that nature will attempt to ensure that there is zero magnetic flux through a closed loop. That is why a current is induced with a magnetic field pointing in the opposite direction. So in this lab we had some real life testing where we dropped the bar magnet through aluminum foil and measured the average time to drop through the roll. And then we followed that up with a computational model to verify those real life results by modeling the aluminum foil as a series of several loops in a long line or a tube to verify those results. Some physical dimensions in this lab was that the aluminum's resistivity was as shown. The next three data points are some important facts about the tube itself, and then these last two are some statistics about the magnet, including the magnet's mass and its dipole moment, which were used in the computational model. So some real-life test results that we got were as shown below. So I dropped the magnet through the tube 5 times and recorded the amount of time that it took. So the average time was 1.36 seconds, and this correlated pretty well with the computational model with a slight difference. So some important considerations when doing the real-life testing was that a ferrous tube couldn't be used because it would produce a magnetic force that would confound the results. It was important to use a conductor, but not a ferrous material in order to get those accurate results. Another thing that we touched on later was that the magnet fell much more slowly than if there were no aluminum foil, and this was regardless of the orientation of the magnet. So next we looked into the computational model, which was done on GlowScript, and here is the graph of velocity versus time. And it took about 1.32 seconds for the magnet to fall completely through the tube. In real life, the magnet made contact with the tube on some of the drops. This is a frictional force that was not accounted for by the simulation, and it caused about a 3% difference between the computational model and real life. So in the simulation, the magnet was dropped with the north pole facing upward. And so in this crude drawing on the left, we showed the magnetic dipole moment through the loop, or magnetic field through the loop, as t increased. So in loops above it, or the blue, as shown in the computational model on the right, the magnetic field dB/dt is less than 0. So using the right-hand rule, Lenz's law and Faraday's law, the thumb points upward, giving a counterclockwise current, which is what the blue current is, and red is simply the opposite, with a clockwise current. To further go on with interpreting the simulation, the dynamics of the magnet does not change when the magnet is flipped, and the computational model slightly underestimated the magnet's time in the tube. Accounting for a small frictional force when the magnet makes contact with the tube would improve the simulation. Furthermore, not assuming a uniform magnetic field throughout the area could also, as due to the bar magnet, could also improve the accuracy. Finally, the shape of the velocity versus time plot indicates to me that the magnetic braking force from the aluminum foil was exactly equal to the weight force. Once the magnet was fully in the tube, velocity was constant, indicating acceleration, and the net force were equal to 0. And some final thoughts for this experiment were, if the resistivity of the conductor were reduced, the induced current would increase. As a result, the magnetic dipole and therefore magnetic force produced by the wire would initially be quite large. Constant speed would be reached much faster. Alternatively, it is also possible that the magnet would actually slow down during its path in the tube, with Fnet less than 0. If there were cuts in the tube, the net effect would be an increase in velocity still. However, the increase in velocity would not match the gain from a simple drop from a height without a tube. There would be drops of free fall punctuated by the braking from the aluminum foil. Thank you for listening.